Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Dr. Raghuram Bharadwaj, and he'll be speaking on algorithms for off-policy reinforcement learning, prediction, and control. Raghuram Bharadwaj is currently working as a senior data scientist at Myntra. He finished his PhD from the Department of Computer Science and Automation, IISc, in 2021. His research interests include reinforcement learning, multi-agent learning, and stochastic approximation. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Bharadwaj directly or type them in the chat box and we'll moderate it with him. Over to you, Dr. Bharadwaj.
Thank you. So let me share my screen. I hope my screen is visible and my voice is audible.
Yes.
Yeah, okay. So good afternoon, everyone. Today I will be presenting about algorithms for off-policy reinforcement learning, prediction and control. This is a work that has been carried out at IISc as a part of my research work. So the outline of the presentation is as follows. I'll first briefly describe or discuss what is reinforcement learning and what is the difference between on-policy and off-policy learnings. And then I'll move on to discuss algorithm for off-policy prediction. So under that, we have proposed a simple and online convergent temporal difference algorithm. And then finally, I'll discuss control problem, that is off-policy control, where we propose a deep off-policy natural actor-critic algorithm. So the first work, off-policy prediction, is in collaboration with Dr. Chandramouli and Professor Shala Bhatnagar, and it appeared at ECI, European Conference on Artificial Intelligence, in 2020. And second work is in collaboration with Pratik Jain, Professor Prabhu Chandran, Professor Shala Bhatnagar, and this appeared recently in IJCN in 2022. So coming to the introduction of 2RL. Before that, let us understand the Markov decision process. So it's a popular process to model the sequential tasks, and it contains the following ingredients of it are S, U, P, R, gamma, where S stands for the state space, U is the action space, P is a probability transition matrix. It says what is the probability of moving from a state S to S dash when action A is chosen. And R is a reward, immediate reward or single stage reward. We can depend on state and action and also next state as well. And gamma is a discount factor representing how important our future rewards are. And we define a policy. A policy is a mapping from state to distribution over actions, telling us what is the action that needs to be taken when we encounter a status. So with these two quantities, we define what is called as a value function corresponding to the policy pi. It is an expected total discounted reward starting from status and following the policy pi. So pi, we are trying to find the value function corresponding to policy pi. So the actions are sampled according to the policy pi. And this expectation is over the states that are encountered from I equal to 1 to infinity. So if we bootstrap it, that is, we take the first term out and then from the subsequent terms onward, if we bootstrap it with value function, we end up with Bellman equations, which is given here, which is expected reward, single stage reward starting from status taking action A, and plus gamma times V pi of S dash, where S dash is the next state. This is for a given policy. So suppose we have a policy and we construct this value functions as here. Now suppose we want to find optimal policy, that is, what is the best policy that can be computed, like what is the best one to be followed. Then we construct Bellman equations for the optimal policy. So earlier the actions here are sampled according to the policy pi itself. Here we have maximum over all the actions that we have and expected reward plus gamma times V star of S dash. In order to solve it, just to simplify it, we construct what is called the Q-Bellman equations. So here in the state S, we have a maximum. In order to push the maximum inside the expectation, the trick that we follow is we take Q-Bellman equations, which is Q of S comma A, which is just expectation reward plus gamma times max of Q of S dash comma B. So V star of S becomes max over B, Q of S dash comma B. Once we solve this, then optimal policy can be computed by just taking argmax of Q of S comma A. Suppose we know the model of the system, that is, we know the rewards, we know the probability transition matrix. So this is the model information. Suppose we know this, there are many techniques in the literature like value iteration or policy iteration to efficiently solve this Q-Bellman equations or Bellman equations and compute the optimal policy. But in real life applications, in practical applications, we often do not know the model of the system. That is, we do not know the transition probability model. We do not know beforehand what are the rewards and each state and action combination and so on. So in such cases, we resort to what is called as reinforcement learning techniques. So RL algorithms learn optimal behavior through interaction from their environment whose dynamics are not known. So in this figure, we see here that there is an agent. It maintains a policy and then it explodes. So the agent takes an action, gives it to the environment, which gives us an observation or state. And based on this information, that is what state the agent currently is in, the action taken by the agent, the reward obtained from the environment, and the transition that happened, that is the next state. Based on this, what we call as trajectory or this information, S, A, R, and S dash, RL algorithm improves its policy. So updates its policy. So the way it does, there are so many algorithms that describe how to update the policy based on this information. So RL agent algorithms deal with taking this information, that is S, A, R, H dash, and improving its policy. So let us look at one example of how it does. So this is from one of our papers on an environment called lunar lander. So here the objective is for this rover to land between these two poles safely, that is without crashing, quickly, that is as much fuel use as possible, and between these two goalposts. So initially the policy will be bad. So it just randomly moves in various directions, crashes, all sort of exploration happens. So these are the initial policies. So here we see that it is crashing sometimes, and sometimes it just moves away, and you will see sometimes that it doesn't even come down. So here you see that it is not. So this is all part of its exploration of the rover. And then the algorithm slowly starts learning. Here you see that it at least starts coming down and at least not crashing. And this here you see that it is coming down safely, did not crash, and landed between the poles. That's good, but it is not quick. It took its own time. So it is coming slowly and it crashed. Finally, at the end of the training, what happens is it comes down quickly, lands safely, and between these two flagpoles. So this is how RL algorithm learns the optimal behavior. Obviously, it doesn't learn this quickly. I have put together various episodes at the beginning, in the middle, and towards the end. So it depends on the sample complexity of the algorithm, the quality of the training set and all. But the trend is same. So essentially it starts with its initial policy, explores, improves its prediction, improves its learning, and finally solves the task efficiently. Yeah. Now let us look at some algorithms to understand what is on policy and what is off policy here. So I just put a full algorithm for the sake of completeness, but the important portions to highlight here is we have an initial policy, and then at each iteration of the episode, we generate, each iteration of the algorithm, we generate an episode from the current policy, pi n. And then this is the training algorithm step. So this is essentially by applying the concepts of stochastic approximation to the Q-Bellman equation, we essentially end up with this scheme. So the algorithm SA stands for state, action, reward, next state, and action. So that's what we are having here. So we update this Q value, and notice here that the Q value of the next state is also sampled from the current policy itself. So AT plus 1, AT, ST, and ST plus 1, everything is generated from the policy pi n itself. So this is very important to note. And once this loop is done, we improve the prediction. Initial policy, generate the samples, run the training algorithm step, and improve the policy. So this is how. So this is the on policy, because everything that is state, action, the next state, and next action are all generated from the same policy that we are maintaining, which is the current policy pi n itself. This is the SARSA algorithm. Now let's look at the popular Q-learning algorithm. We all know that it is an off policy. For the reason we can see here. So the major difference here is, earlier the action for the next state is sampled from the policy itself. If you see here, it is QST plus 1, AT plus 1. But here, the action is just max over Q value. So essentially, we are generating the sample from the current policy and improving the optimal policy. So Q-learning tries to find update or find out the Q values of the optimal policy. So we are having one policy for generating the samples, and we are having the update rule for updating the optimal policy. And hence, for this difference and the reason, Q-learning is an off-policy algorithm. And one more variant or one more category of reinforcement learning algorithms called actor-critic, which we'll go into much detail later, because my second work, that is of policy control, is using actor-critical itself. But just to give you the flavor, it's a gradient-based algorithm. So it uses what is called as policy gradient. And here we have two architectures called actor and critic. And actor is responsible for improving the policy, and the feedback for the how good the policy is provided by the critic. And again, as we can see from this paradigm, it is on policy algorithm, because we have a policy that is computed by the actor. Critic gives the feedback on it based on the how good or bad the policy is, and then actor improves it. So there is still one policy, and we are progressively improving it towards an optimal algorithm. So in this way, we have algorithms which are on policy and then off policy. So just to summarize, in on policy setting, the algorithm evaluates and improves the learning policy itself, whichever it is learning. On the other hand, in off policy, we have two policies. One is called target policy, and one is a behavior policy. Behavior policy is where the samples are generated, and target policy is what we want to learn. Earlier, in our previous Q-learning algorithm, the behavior policy is the current estimate of the policy, and target is the optimal policy. One important thing to notice here is the Q-learning algorithm we have seen is off policy, but there are much more branch of off policy. In the earlier algorithm, the samples are generated from old data, that is previous data, past data. If you look at deep Q-learning algorithms, we maintain something called experience replay, and the samples are sampled from that experience replay buffer. It's still the data generated from the previous policies. But in general, in off policy, the behavior policy can be completely different from the target policy. So behavior policy can be one thing, and target policy can be completely different thing that we are evaluating. So that's, I mean, off policy is a very general case of it. So what are the advantages? Like off policy, we can come up with very sample efficient algorithms. In off policy, the algorithms are not necessarily sample efficient. It depends on the quality of the input data, that is the exploratory data that we have at hand. But the advantages, we can leverage historical or past data as well, which is not possible in on policy setting. However, the advantage here is on policy can be dangerous in many real life settings. For example, consider medical research or automated cars, so self-driving cars. In such cases, this exploration part, right? So that is maintaining a policy, exploring it, acting on it, and then collecting the feedback. It's dangerous. Like we don't want to risk anything in such settings, critical settings. Then in such cases, the only possible solution is to leverage historical or past data and develop solutions. And that is the beauty of off policy. It allows us to use or reuse the data that we already have for that particular application, and then run our algorithm to compute the optimal behavior. Now let us come to the off policy prediction chapter. So in this work, we consider the problem of off policy prediction in RL. As just to reiterate, in off policy, we have two policies. One is target and behavior, and data comes from behavior policy. And the objective here is to evaluate target policy. That is why it is called a prediction task. We have behavior, and we know we have a policy at hand called target, and we want to evaluate it. Evaluate in the sense we want to find out what is a value function corresponding to that policy. Now, earlier we have been seeing the tabular methods. We have seen SARSA, Q-learning. We have seen that Q of S, A. So we are essentially storing the what we call as matrices, so Q of S comma and so on. But these tabular methods are not feasible when we have very large state and action spaces, naturally. So on-policy TD methods are shown to be stable and convergent under linear function approximation. We would resort to function approximation techniques in order to compute the value function, and on-policy TD methods are stable and convergent. But the problem is off-policy TD algorithms can diverge. In this work, our contribution is to propose a simple, online, off-policy TD learning algorithm with linear function approximation, and we prove its convergence. Coming to the complexity part, our algorithm has linear per iteration computational complexity in number of parameters. And we also show the empirical performance of our algorithm and compare it with existing off-policy algorithms like emphatic TD and gradient TD family algorithm called temporal difference correction on standard benchmark RL tasks. So let us revise some of the settings again. So we have an MDP, state space, action space, transition probability matrix, single stage reward, and discount factor. And we are also given a target policy in the prediction. And objective is to estimate the value function of this target policy, which is given in the expression 1. Now, because if the number of, we have under the approximation setting where we assume that number of states are very high, what we do is we approximate the value function as V hat of S and is approximated by Q transpose phi of S, where theta is the, theta transpose phi of S, where theta is a parameter that we would like to optimally find, and phi of S is the parameter, is the features corresponding to the status and the data. Now the behavior, the policy, the data comes from a policy called behavior policy, from which we generate these samples, that is state, next state, and reward. Action is not mentioned here because we know the policy anyway. So action is just mu of Sn. So this is the sample that we have, and using this data, we want to optimally estimate theta. Before going to what are the issues with off-policy TD, let us look at what is on-policy update. So this expression 3, which is given by theta n plus 1 equal to theta n plus step size times reward plus gamma time. This is an approximation for the value function corresponding to the next state, and this is approximation for the value function corresponding to the current state, and this is the features corresponding to the status n. So this is the on-policy temporal difference 0 update. It can be rewritten as in the matrix form given here, theta n plus 1 equal to theta n plus step size times bn minus an theta n, where an and bn are as given. Now, any algorithm with the update rule given in 4 is stable if the matrix A, which is limit expectation of an, which is given in expression 5, is positive definite. And we can show that this matrix, right? So this theta transpose d pi into I minus gamma p pi phi is positive definite in the setting of on policy TD0, and hence this algorithm given by expression 3 is actually stable and convergent. Suppose we want to extend the same algorithm to the off policy setting. So the difference here is earlier the actions are generated from the same policy pi n itself. So we have a target policy, and the samples are also generated from the same target policy pi itself. But here the samples, the state action, next state samples are generated from behavior policy. Therefore, we have to correct for the discrepancy in the action distribution. Therefore, one would add a importance sampling ratio. So this essentially corrects for the discrepancy or difference in the distribution of the actions chosen by both policies, pi and mu. So we multiply this here, and then we try to see what is the corresponding matrix A for this algorithm. And it turns out to be this, phi transpose d mu into I minus gamma p pi into phi. So earlier it was d pi, now it is d mu. That is it essentially a matrix. It's a diagonal matrix where the diagonal entries are stationary distributions corresponding to the policy mu here, and stationary distributions corresponding to policy pi here. The problem is this matrix need not be positive, is not positive definite in general. And that is where we have issues of divergence and not being stable. So what we propose is we add a perturbation term here. The rest of the terms are same. We just add a perturbation term, which is 1 plus eta times phi of Sn transpose phi of n in addition to the previous update. And then if we look at what are the corresponding an and bn for this particular update rule, we actually see that this matrix A is positive definite. So essentially, we look at what is the issue, like what is happening with that previous update rule, why it is not positive definite. We analyze it, when we come up with a term which is called as perturbation term, which essentially makes the matrix positive definite. So in step one, in the which I'm just giving a sketch of convergence analysis. So if we apply limit n tends to infinity of the previous an, we end up with this matrix A, and then we have B to be this. And then we use a couple of lemmas. The first one is, given a k cross k matrix M, it is positive definite if and only if the matrix M plus M transpose is positive definite. So we leverage this lemma, and also we use this corollary called M equal to, if the matrix is of form D into 1 plus eta times I minus gamma p, and if eta is greater than this particular quantity, then this matrix is positive definite, which is the case here. So we make use of these two lemmas and prove the convergence of our algorithm by showing that this matrix A is positive definite. Now, important thing to look at is, what is the point of convergence? We know that it is stable now, and we want to see where it converges to. Any algorithm of the form that we discussed earlier converges to a point called point where B minus A theta star is equal to 0. In our case, it turns out to be this. So the theta star satisfies, like if we expand B minus A theta star equal to 0. So we see that similar to the online on policy TD0, our online off policy variant also converges to fixed point of the projected perturbed Bellman operator. So earlier we have just Bellman operator, projected Bellman operator. With this introduction of the perturbation term, the fixed point is essentially projected perturbed Bellman operator, which is pi d mu into t pi eta. Coming to the experiments, we want to see how good it works on the standard divergent environments. So what we do is we perform experiments on two benchmark counterexamples for off-policy divergence. These environments are where the standard off-policy algorithm diverges, and also on a three-state MDP example where the value functions are non-trivial. And as introduced earlier, we also compare with standard off-policy, emphatic TD0, and temporal difference correction algorithm. One important observations that we need to have here is the bound that we derived for eta is sufficient but not necessary condition. That is this eta bound. It is important, it is sufficient, but it is not necessary for a convergence. If the value of eta is large, the algorithm still converges because we are still respecting this condition, but it converges to a poorly approximated solution. So therefore, eta is to be treated as a hyperparameter. We will see the importance and the relevance of eta in our experiments, and choose a value that is large enough to ensure convergence and is small enough so that we make sure that the approximation is very close. So first example is called theta to 2 theta. The important thing to note here is we see that the standard off policy TD0 diverges. So it's just going up. And the rest of the three algorithms of off policy, that is emphatic TD, TDC, and our proposed perturbed off policy TD0 converges. Converges to a point where the error is 0. So that's very important. And next is very popular Baird's counterexample. So here we can see that first important thing to note is standard off policy TD0 just diverges. And then our perturbed off policy TD0 and TDC converges. And we also saw that the emphatic off policy TD0 is oscillating. I mean, it's coming down, coming up, and there are some oscillations in that algorithm. And the three-state MDP, in the previous two examples, the optimal value functions are 0. So therefore, we wanted to check on an example where the value function is non-trivial, that is, value function is non-zero. And even here, we see that number one observation, the standard off policy TD0 diverges. Number two, the perturbed off policy TD0, that is the proposed algorithm, and TDC converges. But our algorithm seems to be faster compared to the TDC algorithm. And like before, the emphatic off policy TD0 still is oscillating. So as I was talking earlier, what is an effect of eta? If eta is large, like the optimal eta for the previous task was 0.5. In 0.5, we see that it converges nicely and quickly, and its RMSE is minimum. Now, if we select any value of eta greater than 0.5, we still converge. which can be seen by when eta value is 0.6, it still converges, but a not as good solution as possible because the RMSE value, that is error value, is slightly higher compared to when eta equal to 0.5. On the other hand, if we do not respect the condition, that is condition on eta, that is if we choose a value which is smaller than the ideal, that is 0.4, it diverges. So this is very important to note that selecting an optimal value of eta is very important to ensure convergence 0.1 and 0.2, convergence to a solution which is a close approximation to the actual solution. So in this work, we proposed an off-policy TD algorithm for mitigating the divergence problem that is associated with the standard off-policy TD. And to do that, we make use of perturbation parameter to ensure the convergence. So what this perturbation parameter is doing is, it makes the matrix positive definite, which will give us the convergence. As I was discussing earlier, the choice of eta is very critical, and the lower bound that we have provided is not tight. And coming up with a tight bound is a very important future direction. And another important direction is to extend our algorithm to include eligibility traces. That is, earlier we have been talking about TD 0, right? So 0 is where, the place where 0 we can have lambda, it's called temporal difference with eligibility traces. And then we can generalize it to TD lambda algorithms, and then we study its applications on real world problems. So this is the work corresponding to the prediction problem, where we have a behavior policy from which samples are generated, and we also have a target policy that we would like to evaluate. But in many of the real world or practical applications, one would like to compute an optimal policy from the behavior policy. That is, we have a policy that our historical data that we would like to leverage and compute optimal policy itself. So this is from this work by Pratik, Professor Prabhuchandran, and Professor Shala Bhatnagar, and it appeared in IJCN in 2022. In this, the contribution is convergent, efficient, and flexible RL algorithm to solve both off-policy and non-policy learning problems here. So we will come to each of the terms, like how convergent it is, what is efficiency, and what is the flexibility. And the salient features of our algorithm are, we make use of what is called as compatible features to ensure convergence, and we use deep neural networks to have generalization, and we use natural gradient to ensure speed. So these are the salient features of our proposed algorithm, and it works well both in on-policy setting and also off-policy setting. Let us define some quantities. We define pi theta. So notice here that we are parameterizing pi with theta, and in order to compute the optimal policy, as discussed earlier, we are going into the policy gradient scheme, that is making use of actor-critic, where we have an objective function j in terms of theta, and we try to update our optimal, we would like to update this theta value and make sure it goes towards convergence. So the policy is parameterized here, and as earlier, policy tells us the distribution of actions to be chosen in given status. Associated with the policy, we define a policy metric j pi theta, which is again expected discounted reward, where the initial state is sampled from initial distribution and action is corresponding to the current policy pi. And we multiply 1 minus gamma as a normalizing factor here. And then the objective of the RL agent, once that we have a performance metric, is to compute an optimal policy that maximizes j of theta, that is theta star, which is argmax of j of theta. And then we have a very celebrated policy gradient theorem, which actually gives us a closed form expression for gradient j of theta, which is expected, state and expectation of state and actions, grad log pi of SA. So this is called compatible features corresponding to status and action A. And A pi of S comma I is called advantage value function corresponding to status and action A. And the distribution D tilde is a discounted stationary distribution under the given policy pi theta. Now, naturally, what we would like to do is we would like to approximate this A pi of theta as well, because we are in the setting where the number of states and actions are very large or can be infinite as well. So we approximate A pi of S comma A with X transpose compatible features. So the very important point to note here is we do not arbitrarily select the features for the advantage value function. Earlier, we have seen that theta transpose some phi of S, where phi is the features corresponding to the status. But here, for the convergence, it is important that it is necessary that the features corresponding to status and A are in fact the compatible features, that is grad log pi of S comma A. In such cases, one can write policy gradient theorem to be F into X star, where F is given to be this Fisher information matrix, and X star is the optimal projection of advantage value function onto the compatible features. Now, let us look at, now that we know what to do, so we have all pieces with us, like we want to approximate grad J of theta. We have this expectation. We are again approximating A pi of theta. Now we have some choices to make on how to apply all these pieces. Now, suppose we come up with an actor-critic algorithm with arbitrary architectures. That is, actor may be using one neural network and critic using a different neural network, not respecting this constraint. That is, the features to be grad log pi of S comma A. Then it is unrestrictive in the sense that it can make full use of neural networks and compute optimal solution. In fact, in practice, we see that in fact it works well, where actor and critic using different neural networks, we can run some RL tasks and still get optimal solution. But there are no convergence guarantees. We can't ensure that the algorithm converges. On the other hand, if we have a restriction that is saying that actor and critic have compatible architecture, that is, the critic can use nothing but this grad log pi of S comma A, then we have convergence, because the policy gradient theorem will give us the convergence. But the issue is it is not unrestrictive. That is, the critic is not making full advantage of the neural network. So in order to solve that, what we use is we make use of one actor and two critics. We name one critic to be advantage critic and other to be value critic. We will see that in more detail now. So we have an actor, and earlier at the beginning of the discussion, we saw that there is only one critic which evaluates how good the policy is. But in our proposed scheme, we have two critics. One is called advantage critic and one is a value critic. The responsibility of the value critic is to compute the value function, just the value function, and pass it to the advantage critic, which computes the parameter x, that is this parameter x, and gives it to the actor for improving its policy parameter theta. The important point to note here is, while the advantage critic has to have this compatible features as its features, value critic is pretty much independent. So here we can leverage the power of neural network, compute the value function optimally, pass this information to the advantage critic, which is restrictive. That is, it is still a linear network with features as grad log pi of S comma A, and then we update the critic parameters and give it to the actor critic. So in this way, we are trying to achieve convergence. Then we are making full use of neural networks in this proposed architecture. Next question arises is, what about speed? We achieved flexibility, we achieved convergence. The next thing is speed. So for that, we move to the natural gradients. So now we have theta. We know update rule for it. We have all the things in hand. Now one would like to use the gradient algorithms in order to update theta. There we have a choice of using standard gradient algorithm, that is gradient ascent, or natural gradient algorithm. Just to highlight the differences, in standard gradient, the gradient update will be happening in a parameter space, whereas natural gradient works in a distribution space. And I mean, some of you who would have implemented would have seen that in standard gradient algorithms are highly sensitive to hyperparameters. So especially when neural networks are involved, one would have to do a very high level of hyperparameter tuning in order to converge to right set for speed, convergence, and good solution. Whereas in natural gradient setup, the parameters are less sensitive. The updates are less sensitive to the hyperparameters. The reason being, standard gradient algorithm doesn't use any curvature information, whereas natural gradient makes use of the curvature information. Therefore, it uses second order information for updating its parameters, and hence it is shown in the literature to be faster compared to the standard gradient. Now, another advantage that we have is, when we take the natural gradient setup and apply it to the actor critic, we end up with a very simple update rule. So in standard gradient algorithm, we just have grad J of theta. In natural gradient, we have F inverse grad J of theta, where F is a Fisher matrix that we have seen earlier, this. And then if we just substitute what is grad J of theta, we have F inverse of theta into F of theta into X star, which is simply X star. So The update rule is very simple for the actor. It's just once we compute x, we can use the same x in order to update my theta value. So putting all these pieces together, first we have to compute what is x star. So it can be computed by calculating them by minimizing this squared loss between actual value function and approximated value function. So x star must satisfy the optimality condition where grad of L of x is equal to 0. I mean, obviously, we do not know a pi of s comma a. If we know, we wouldn't be even doing this minimization. So we again approximate a pi of s comma a with r plus gamma times value function corresponding to s dash minus value function corresponding to the status. And then we substitute it in order to find the optimal x star. Now the next missing piece is how do I compute v pi? Here is where the value critic comes into picture. The value critic learns or trains the optimal value function by minimizing this temporal difference 0 loss, which is given here. So this is the loss, and then by taking the gradient of it and updating the value function in the direction, we try to minimize this loss and compute the optimal value function. So we have seen that we have a value critic, computes value function, passes it to the advantage critic, it computes x star and gives it back to the actor, which simply consumes it and updates its theta value. So this is how it happens. So we have the parameters theta corresponding to the actor, psi corresponding to the value critic, and x corresponding to the advantage critic. So in each step, what we do is we select an action from pi theta of s. This is important because we are still in the on policy setup. The actions are sampled according to the current policy itself. And then the environment will give us the next state and reward. And this first step, we construct what is called as a TD0 term. So this is the TD0 term. And then value critic does this update. It is for psi, updates the value of psi, gives it to the advantage critic, which then updates the value of x. And then it is passed on to the actor, which is simply updating, running the natural gradient and updating its theta. So this three updates will be happening in each stage until we achieve the convergence or optimal policy is obtained. This is the on policy setting. Still, we haven't gone to the off policy. So just to summarize, what we are doing is we are achieving the convergence by respecting the constraint on the compatible features, and we are using neural networks to make sure that we are generalizing well, that is value function is best approximated, and then we are using natural gradients in the actor update to ensure speed. So applying these three concepts, just like how we apply to on policy and extending it to the off policy, is our next work. The difference here is in off policy setup, we have a behavior policy mu from where the samples are generated. So the samples here, SCA and S dash, are generated from the behavior policy. This is the distribution corresponding to the behavior policy, and actions are sampled from the behavior policy. And now what is the difference? Like we have seen in the prediction as well, there is a mismatch in state and action distribution. So that is what we would have to correct. Just to see how we actually manage this discrepancy, the important portion to note here is earlier we have seen this L of x, where the loss function corresponding to the advantage critic. Here the state and actions are sampled from the current policy pi theta itself. Now somehow we have to end up with state and action sampled from behavior policy. The way we do is we just expand this d tilde pi theta into pi theta, and this is the rest of the terms, and then we multiply and divide by d mu of s and mu of s comma a. And suppose we will see how to compute w theta, but suppose we know what is w theta of s, and rho of theta is just a ratio of actions, that is fine. And suppose we know how to compute w theta of s, then we are good to go. So in fact, we can do the same grad of L of x by having samples S and A coming from the behavior policy now, given that we know what is W of theta. Similarly, for value critic as well, we use the same trick, multiply and divide by the ratio of distributions, and essentially convert this expectation from the current policy pi theta to behavior policy mu. So, and again, assuming that we do know how to compute W tilde. The difference here is W tilde is ratio of stationary distributions, and W is the ratio of visitation distributions. Fortunately, in the literature, we do have estimation techniques for efficiently computing this W theta and W hat of theta. So we essentially leverage these algorithms from the literature and compute it, and then sample the states and actions from behavior policy and do the same thing as before. So just quick summary of like how this W hat is estimated. I mean, this is not our work. This is from the literature. So what in the work given here in this work, the authors, what they do is they compute the W theta, W hat by showing three important theorems. So first, they have an expression saying the stationary distribution stationary distribution. So it satisfies this equation 27, and then any W which satisfies this, right? So this expression. Then if it satisfies, if and only if it is an optimal W star. So this is the first theorem that they prove. It is just by manipulating this expression 27, multiplying and dividing again by d mu of s dash and so on. They end up with this theorem 1. And then they formulate a loss function based on this. So how they do is, here there is a conditional distribution on s dash, right? So we multiply with f of s dash corresponding to the distribution on both sides, and the function with respect to the function f, and we end up with this loss function. Now W star is estimated by solving min max of L of WF whole square. So suppose we fix a W, and then we try to find what is the max of L of F comma W. If it's a large number, then we would have to come down because we want to minimize this L of W comma F. So we have W, we try to find the W which is min max of L of WF whole square. So that's the core idea of the procedure proposed by this proposed in this paper. And then now again there is an issue. The issue is like this has to be satisfied for all functions. But how do we do it for all functions? Like how do we compute maximum over all functions f? Hence, what they do is they again do an approximation. This maximization part can be approximated to obtain closed form expression given by here, where k is a kernel which measures the distance between the current state s dash and s bar dash. So in this way, this paper efficiently estimates the ratio of stationary distributions. Similarly, the paper itself proposes the way to estimate discounted visitation distribution as well, that is W. So we make use of these two estimation algorithms and estimate our ratio of distributions. So again, like before, the algorithm proposed in the paper, what it does is it makes use of this transition data set, state, action, next station, r dash from the simulator, which are generated from the behavior policy, not the current policy, and tries to have this update rule. So this is essentially approximating this expectation, and then try to compute the optimal parameters W. So putting all these pieces together, earlier we had this portion, that is in on policy, behavior policy for generating the samples, value critic, which computes mix value function, passes that information to advantage critic, which estimates X using the compatible features given from actor, and then the actor updates the policy parameters theta. Now, because there is a discrepancy of state and action distribution, value critic has to include this W hat, which is estimated using the stationary distribution ratio estimation network. And then advantage critic also have to correct for this discrepancy, and hence it uses W theta, and this is given by this discounted visitation distribution ratio network. And by leveraging this information, we efficiently estimate the actor parameters. So just to recap here, like before, it runs in iterative procedure. We first estimate W theta and W hat. This was not there in the on policy because there we didn't have to correct for any discrepancy. An important point to note here is actions are sampled from the behavior policy now, not from the current policy that we were doing in the on policy setting. And then we generate next state and reward from the environment. This is similar, and see the difference here. So earlier we just had psi equal to psi plus alpha step size times delta grad v, but because of the discrepancy we have two more terms, which is ratio of state distributions and ratio of action distributions multiplied to correct for the discrepancy. Similarly for advantage critic as well, we correct for the discrepancy in the distributions. Now actor we don't have to correct because we know the natural gradient setup, which is just simply the optimal advantage parameter x itself. So it is still the same as before. And this is how we come up with an off-policy deep natural actor-critic algorithm. So let us look at some results. So we tested our algorithms on 4 standard benchmark RL tasks. First is the cart pole. So here we have a pole, and the objective is to balance this pole on the cart by moving either left or right for a maximum of 500 time steps. And then we have second task called acrobat, where there is a robotic arm with 2 joints initially hanging downwards, and the objective is to move the lower arm above a prescribed height using its own momentum. So that is the objective in the acrobat. And third is a mountain car, where a car is placed at the bottom of the mountain, and the objective is to make this car reach the top of the mountain, that is its goal post, using its own momentum. So it has to go left and right, and it has to generate its momentum, and finally go back till the back and then climb top. So using its own momentum, we would like to make this car reach the top of the mountain. And fourth is lunar lander, which the experiment we have seen earlier, the demonstration. We have a rover whose objective is to come down slowly, safely, and between these 2 flagpoles. So we first tested on the on policy setting. So here first on the top, these are the results are during the training, and in the table we have put the results of the convergent policy on testing. Here we see that for the majority of the tasks, on policy algorithm converges faster compared to the natural actor-critic algorithm converges faster compared to the standard actor-critic algorithm. Similarly, even during testing, the natural actor-critic gives better results on majority of environments compared to the standard actor-critic algorithm. Similar to on-policy results, even in the off-policy setting, we see that the deep of natural actor-critic converges faster compared to the standard actor-critic, and during the testing as well, we get better results compared to the deep off-policy actor-critic algorithm. So coming to the conclusions, in this work, we first proposed a non-policy compatible deep natural actor-critic algorithm. We then extended the algorithm to the off-policy setting, that is off-policy compatible deep natural actor-critic algorithm. And in future, we would like to conduct ablation studies to understand the impact of this these 2 components, that is distribution ratio networks. So how important it is to correct for the what happens if you don't correct for the state but correct for the actions, and vice versa, and so on. So we would like to conduct ablation studies to understand the importance of these 2 networks. That is the part of our future work. And I would like to thank the Center for Network Intelligence for giving me a fellowship grant, and these works are supported by this fellowship grant. And thank you very much. If you have any questions, please let me know.
Thank you, Dr. Bharadwaj, for an informative talk. We can take a few questions now. Are there any questions?
I had a question, Raghuram. It's not directly related to your work, but in general about the RL models and especially DNN models. When you're applying it to some realistic problems, usually it's said that there are like explosion of the number of tunable parameters. So what is your experience in this? Like how many parameters do you need to tune?
That's a good question, actually. So it depends on the complexity of the problem that we have at hand. Even in the experiments that we have seen, right? For cart pole, we just need to, even one layer of network, in fact, linear network itself suffices. We just take linear network and then try to compute the solution efficiently. But if you go to lunar lander, tasks like lunar lander, then it's again exploration. We have to see how many neurons needs to be used in each layer, and how many layers needs to be used, and what are the activation functions that one would have to use, and so on. So in this paper, actually, what we did is, there are not only the architecture to finalize, we have to decide on the activation functions, then we have to tune hyperparameters. So at least we thought, let us solve one problem, that is by using an efficient algorithm like natural gradient descent or ascent, we are essentially solving one problem of hyperparameter tuning. Because if we just use natural actor critic, I mean, in fact, we have seen in practice that it's not very sensitive to hyperparameters. So at least that problem is solved, but the architecture design and the activation functions will still depend on the task itself, task at hand, how rigorous the approximation needs to be and how important it is. So my opinion is it differs from task to task.
Thank you.
Thanks.
Are there any other questions? Okay, if there are no other questions, then we can wind up today's session here. Thank you, Dr. Bharadwaj, again for agreeing to speak at the CNI seminar series.
Thank you.
And as discussed before, we'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. Please do check. Thank you and have a great evening.
Thanks. Thank you, everyone. Thanks for the invitation.